Every reliability model makes a structural assumption about how components fail. The Weibull distribution assumes failure rate follows a power law relationship with time. The Arrhenius model assumes failure rate scales exponentially with temperature. Fitting parameters to failure data is not the same as validating the structural form. A reliability model can fit historical failure records and still be structurally wrong for new operating conditions. The confusion between parameter fitting and structural correctness is the origin of model risk in reliability engineering. The exponential distribution assumes a constant failure rate. Failures are equally likely at any age. For components that exhibit wear-out, the failure rate increases with time. Applying an exponential model to a wear-out failure mode is a structural misspecification. The model will fit early operational data reasonably well, but it will systematically underestimate failure probability as components age. No recalibration of the rate parameter corrects the wrong structural assumption. With more failure data, parameter estimates become more precise. Shape and scale parameters of the fitted distribution converge. But if the structural form is wrong, exponential when the true process is Weibull with increasing hazard, more data does not help. More observations reinforce the wrong structural form. The model becomes more confidently wrong about the failure rate at the ages that matter most. Data volume does not substitute for structural correctness. Maintenance schedules are optimized against a degradation model. If the degradation model assumes constant failure rate when wear-out is the true process, the optimal maintenance interval is wrong. The more precisely the schedule is optimized, the more precisely it is timed to miss the actual failure mode. Components fail between scheduled maintenance because the structural model predicted they would not. High scheduling precision inside a misspecified degradation model worsens reliability. It does not improve it. A reliability model can pass AIC selection and chi-square goodness of fit tests and still be structurally wrong. Fit statistics measure how well the model reproduces the observed failure data. They do not measure whether the structural form holds under operating regime changes. Two models with fundamentally different failure rate structures can produce indistinguishable fit statistics on the same dataset. When operating conditions shift, higher temperatures, new duty cycles, aging components, structural differences emerge. In-sample fit cannot resolve structural uncertainty. When components are deployed in new environments or duty cycles, the operating regime changes. Reliability models fitted to prior operational data may be structurally wrong for the new conditions. Structural failures in reliability models are often invisible until the regime change has already occurred. Model risk in system reliability is managed by structural humility, using multiple model structures and scenario testing. Structural humility in system design means preserving optionality, avoiding designs that are fragile to structural model failure. Treating a reliability model as true eliminates protection against the failure mode you cannot see.